Hi, welcome to educator.com. We're going to talk about ANOVA with independent samples today. So first, we need to talk a little bit about why we need to introduce the ANOVA. We've been doing so well with Ttest so far, right? Well, there are some limitations of the Ttest, and that's why we're going to need an ANOVA here. An ANOVA is also called the analysis of variance, and the analysis of variance is really also could be thought of as the omnibus hypothesis test. So it's still a hypothesis test, just like the Ttest, but it's the omnibus hypothesis test, and we're going to talk about what that means. We're going to need to go over a little bit of notation in order to break down what the ANOVA entails. And then we're really going to get to the nitty-gritty of partitioning or analyzing variance, right? Like getting down and breaking apart variance into its component parts. Then we're going to build up the F-statistic made up of those bits and pieces of variances, and then finally talk about how that relates to the F distribution and hypothesis testing. Okay, so first thing, the limitations of the Ttest. Well, here's a common problem. Like, we might want to know this question, who uploads more pictures to Facebook? Latino users, white users, Asian users, or Black Facebook users? Which of these racial or ethnic groups uploads more pictures to Facebook? Well, let's see what would happen if we used independent samples Ttest. What would we have to do? Well, we'd have to compare Latinos to whites, Latinos to Asians, Latinos to Blacks, and then whites to Asians, and whites to Blacks, and Asians to Blacks, right? And it's like, whoa, all of a sudden, we have to do 6 different independent samples Ttest. That's a lot of tiny, tiny little Ttest. And really, the more Ttests you do, that increases your likelihood of type 1 error. Previously, to calculate type 1 error, we looked at 1 minus the probability that you would be correct, right? So 1 minus the probability of being right. And that was something like 0.05, let's say, right? But now that we want to calculate the probability of type 1 errors for 6 Ttests, we have to think back to our probability principles. But really, alpha is going to look something like this. 1 minus whatever your correct rate is to the 6th power. And that's going to be a much higher type 1 error rate than you really want, right? So the problem is that the more Ttests you have, the bigger the chance of your type 1 error. And even non-mathematically, you could think about this. Every time you do a Ttest, you could reject the null, right? Every time you reject the null, you have a possibility of making a type 1 error, right? And so if you reject the null 6 times, then you have increased your type 1 error rate because you're just rejecting more null hypotheses. So you should know there are 2 major limitations of having many, many tiny, tiny little Ttests. So if you have 6 separate Ttests, one is the increased likelihood of type 1 error, and that's bad, right? We don't want a false alarm. But there's a second problem. You're not using the full set of data in order to estimate S. Remember how before we talked about how S is an estimate of the population standard deviation? Well, it would be nice if we had a good estimate of the population standard deviation. And you know when you have a better estimate of the population standard deviation? When you got more data, right? When you do a Ttest, for instance, with Latinos and white people, then you're ignoring your luscious and totally usable data from your Asian and Black American population, right? So that's a problem. You're ignoring some of your data in order to estimate S. And you're estimating S a bunch of different little times instead of having one sort of giant estimate of S, which would be a better way to go. So both of these are major limitations of using many, many little Ttests. So back in the day, statisticians knew that there was this problem. Ronald Fisher came up with a solution, and his solution is called an F-test. F for Fisher. Ta-da. If you think of a new statistic, you could name it after yourself. So he thought of something called an F-test, but this F-test also includes a new way of thinking about hypotheses. And so the F-test could also be thought of as an omnibus test. And the way you could think about them is like the Lord of the Rings ring idea. It's one test to rule them all. Instead of doing many, many tiny, tiny little tests, you do one test to decide once and for all if there's a difference. And because you have this one test, you need one null hypothesis. And here's what that null hypothesis is. You need to test whether all the samples belong to the same population or whether at least one belongs to a different population, right? Because remember, the null hypothesis and the alternative hypothesis, they have to be like two sides of the same coin, right? So your null hypothesis is that they are all equal. The mu's are all equal. They all came from exactly the same population. The other hypothesis, the alternative hypothesis, is that they are not all equal. But let's think about what that means. That means at least two of them are different from each other. It doesn't mean that all of them are different from each other, but it means at least one guy is different from one of these guys, right? That's it. That's all it means. That's all you could find out. So let's consider this situation. Let's say you have these three samples, right? Your null hypothesis would be that they all came from the same population. A1, A2, and A3, all the same population. A, right? But if we reject that null hypothesis, what have we found out? Well, we have found out that at least two of them differ. At least. All three of them could differ from each other. Or it could just be two of them. It could be that A1 and A2 are the same, but A3 is different. It could be that A2 and A3 are the same, but A1 is different. It could mean that A1 is totally different from A2, and that's totally different from A3. Any of those are possibilities. So here's the good thing. The good thing about the omnibus hypothesis is that you could test a whole bunch of things at once, right? That they all come from the same population. You could test that big hypothesis at once. The bad thing about it is that if you reject the null, it still doesn't tell you which populations differ. It only tells you that at least one of the populations is different. That's it, right? So when you reject the null, it's not quite as informative, but still it's a very useful test. Okay, so we need to know some notation before we go on. In analysis of variance, right? So analysis of variance, that's why it's called the ANOVA, right? So sometimes you might see it with the O being little. ANOVA notation, you want to analyze the variance, right? So when we want to analyze the variance, we have to really think hard about what variance means, right? And variance is sort of the average spread around some mean, right? So how much spread you have. Are you really tightly clustered around the mean, or are you like really dispersed around the mean? Okay, so first things first, consider all the data that we get from all the different groups. Let's say we have 3 groups, all the data from all the different groups. There's a lot of variance around the grand mean, and the grand mean is a new idea. The grand mean is not just the mean of your sample, but the grand mean is the mean of everybody lumped together. Pretend there aren't 3 groups. Pretend there's just one giant group that all 3 data sets have been sort of poured into. What is the mean of that giant group? That's called the grand mean, right? And so for instance, here's our sample from A1, our sample from A2, our sample from A3. And when you have sample means, here's what the notation looks like. This should be pretty familiar. X bar sub A1, right? X bar sub A2, X bar sub A3. Now, when we have a grand mean, we don't have 3 of them. We just have 1, because remember, they're all lumped together, right? How do we distinguish the grand mean? If we just say X bar, we might confuse it for being a sample mean instead of a grand mean, right? And so in order to say grand mean, this is the mean of all the means, right? Mean of all the samples, right? We call it X double bar, right? And that's how we know that it's the grand mean. So that's definitely one of the things you need to know. All right, so now let's talk about partitioning or analyzing variance. Analyzing variance. Well, when we analyze variance, what we want to start with is the total amount of variance, right? Because first we got to have the big thing before we like chunk it apart, right? So what's the big thing? The big variance in the room is total variance. And this is the variance from every single data point in our giant pool around the grand mean. And we could actually just sort of think about how to write this as a formula just by knowing grand mean as well as the variance formula, right? And so variance is always squared distance away from the mean divided by however many data points you have, right? To get average squared distance from the mean. Now, we want the distance away from the grand mean, right? So I'm going to go ahead and put that there. Instead of x bar, I have x double bar, right? And I'm going to put my data points. So that will be x sub I, right? And we want to get the sum of all of those and then divide by however many data points we have. Usually n means the number of data points in a sample. How do we tell it the n of everybody, of all your data points added together? Well, here's how. You call it n sub total, right? And this says it's not just the n of one of our little samples, because we have 3 little samples. I mean the n of everybody, of the total number in your data set. And so even this x sub I don't really mean just the x's in sample 1. I mean every single data point, right? So I would say I goes from 1 all the way up to n total. Sorry, this is a little small, but it says n sub total up here. And so this will cycle through every single x, every single data point in your entire sample lumped together. Get their distance away from the grand mean, square it, right? Add those squared distances together and divide by n, right? And so this is just the general idea of variance, right? Average squared distance from the mean. In this case, we're talking about grand mean, right? And so how do we say total variance? Well, it would be nice if we could say like, oh, this is something subtotal, right? Before we go on to variance, though, I just want to stop here. Before we go on to average variance, I just want to talk about this thing. What is this thing? And so let's talk about variance real quick. So variance is always going to be the sum of squared distances, right? Sum of squares divided by n. Or if you're talking about s squared, it's the sum of squared distances over n minus 1, right? And another way of saying that is ss over degrees of freedom, right? So we're just going to stop here for a second and just talk about this sum of squares, right? And we're going to call that sum of squares total, all right? So that's sum of squares total. And that's going to be important to us because later we're going to use these sum of squares, these different sum of squares, to then talk about variance. But I want you to see sum of squares, very, very related to the idea of variance. Okay. Now, we have this total variance because this is really the idea of how much you're varying, right? We have this total variance and we're going to partition it into 2 types of variance. One is within group variation, and the other is between group variation, right? So if we have 3 groups, the between group variance is going to look at how different they are from each other. The within group variance is just going to look at how different they are from their own group, how different the data are from their own group. And that's going to be important because this sum of squares total actually is made up of sum of squares within plus sum of squares between, right? And so because of this idea, we could really now see, we're taking this whole variance and partitioning it into within group variance and between group variance, or between sample variance. All right, so first things first, within group variance, how do we get an idea of how different each sample is from itself, right? Well, the very idea is just like what we've been talking about before. This is each sample's variance around their own mean, right? And we already know the notation for those means. So that would be something like, how much does everybody in sample A, A1, right, differ from the mean sub A1, right? So what is that difference squared, and getting the sum of squares, right? And what is the variance, right, the sum of squares for everybody in A2 squared, right? And the same thing for everybody in A3, right? So this is sort of the regular use of variance that we've used before, regular use of sum of squares that we've used before. Just looking at each sample's variance from its own sample mean. Now how do we get between group variance? Now between group variance is going to be each sample's mean how much does it vary from the grand mean? Difference, squared difference from the grand mean, right? So there's some grand mean, and how much does each sample's mean differ from that grand mean, right? And so that's going to be between group variation. How much do the groups differ from that grand mean? Okay. All right, so first of all, let's just review variance and sum of squares. So sum of squares is an idea that we're going to use over and over again. And it's just this idea that you're summing, right, the sigma sign, summing something from x bar squared, right? So it's just basically the squared distance away from the mean, and you add them all up, right? That's sum of squares. Now, what we're doing is we're sort of swapping out this idea of the mean for things like grand mean, right? Sample mean, right? Right? And we're also swapping out what our data points are. Is this like from n total? Is it from all the data points? Is it just the n from the sample, right? Is it the group means, right? So we're swapping out these two ideas in order to get our sum of squares total, sum of squares between, and sum of squares within, right? But it's always the same idea. Sum distance squared, add them all up. Okay, now, so what's variance's relationship? Well, variance is the average squared distance, right? And so in doing this, we always take the sum of squares and we divide by however many data points we have. But often, remember, we're using estimates of S instead of actually having the population standard deviation. So we're going to be using degrees of freedom instead of just N, right? And we're going to have different kinds of degrees of freedom for between and within group variation. So watch out for that. Okay, now let's go back to the idea of the F-statistic. Now that we've broken it down a little bit in terms of what kinds of different variances there are, hopefully the F-statistic makes a little more sense. The idea is that you want to take the ratio of the between group or sample variance over the within group variance. And the reason we want this particular ratio is that we're actually very, very interested in the between group difference. That's what our hypothesis test is all about, whether the groups are different or the same, right? The within group variation, we cannot account for. It's variation that just is inherent in the system, right? And so we need to compare the between group variation, which we care about, with the within group variation, which we cannot explain. We don't have any explanation for it, at least not in this hypothesis test, right? You'll have to do other tests to figure out that stuff. Okay, so now that we're here, what we need to do is replace these conceptual ideas with some of the things that we've been learning about. In particular, the variance between and variance within, right? And so variance, we're going to use s squared, right? But s squared between over s squared within, right? So variance between over variance within. But now we know a little bit, like we've refreshed, oh, what is variance about? How can we break it down in terms of sum of squares? Well, that's what we're going to do. We're going to sort of double click on this guy, and here's what we see inside. We see the sum of squares between divided by the degrees of freedom between. All over the sum of squares within divided by the degrees of freedom within. Right? And this is how we're going to actually calculate our F-statistic. Now, we'll write out the formulas for each of these, but it's sort of good to know like where the F-statistic sort of comes from. It's conceptual roots. You always want to be able to go back there. Because ultimately, when we have a large F, you want to be able to say, this means there's a larger between group variation than within group relative to within group variation. A larger difference in the thing that we're interested in over the variance that we have no explanation for.